Hello students, in this tutorial we're going to be looking at some examples on how to determine the components of 3D force vectors. Now let's see the question that we have. In this case, we're being told that for each of the following figures, that's this figure here and the one that is coming below. So for each of the following figures, they want us to determine the x, y, and z scalar components of the resultant force F. And in the second part, they want us to express the resultant force F in Cartesian vector form and determine the direction angles alpha, beta, and gamma. So if you missed the video where we were showing the methods on what these components are, I'll leave a link in the description and then you guys can check it out. So let's quickly go right to the first example and see what we're supposed to do here. For this example, we notice that the force that we've been given is this force and want to find its components. So if we look at the angles that are given, they haven't given us the directional angles alpha, beta, and gamma. They haven't given us what these are. Instead, they've given us the transverse angle and this angle that is this side. So we looked at how we use this method or these angles if they're the ones given. So we'll label this as phi, then we'll take this as theta. So in this case, of course, since the theta down here is practically just in the x and y axis, we know we're just going to treat it the usual way, but in the x and y axis. And then for the other side, we'll get back to it. So let's start with, we can start with either side. Let's start with this triangle. Let's shade it in blue. So let's start with this line that is here. So this creates the base of the triangle that we're forming here with the force vector F. So if I was to isolate that triangle, notice that what we have is the base, which is this, and then we have the vertical part, and then the force vector F being this side. So if we look at this, we are forming a right angle triangle. So the right angle is going to be right down here. So this part, this is F, and from the question, this is 1,000 pounds. And then let's label the base here as F prime. Now, observe that this part is going to be parallel to the z-axis. This is going to be parallel to the z-axis. So it's going to be the z component. It's going to be Fz. So from this triangle, we see that we can already come up with an expression for the z component. So the angle that we have is this angle here. This is the angle that we labeled as phi, the 25 degrees. So this is 25 degrees. So we see to say that this angle is opposite to Fz, so we're just going to go on and say Fz. And then to get this component, the vertical component, it's the vector itself, the 1,000. It's opposite to the angle, so we're using sine. And the angle is 25. So this is how we're going to get the z component. And from here, we do the math and we find 423 pounds. So this gives us what Fz is, but when it comes to the other part, we'll need it later. So let's go right ahead and find it, F prime. So for F prime, it's side by side with the angle, so we're using cos. So it's going to be the force vector itself, which is 1,000, then cos the angle 25. So this is what F prime is. So from here, we then move on to the rest of the sides. So for this part now, let me remove everything else and look at what we have left. Notice that we can create another triangle at the bottom. The triangle that we create now is going to have this piece going this side, and it's going to have a face that is this side, and another face that is going to be along the y-axis. The piece that is going to be parallel to the x-axis is going to be this one, so this will be giving us F in x. And this piece here is parallel or literally along the y-axis, so this one will be giving F in z, in F in y I mean. The angle here that we'll be using, we can use the 130, but notice that we can also use just this angle here. And since the whole thing is 130, and we know from here to the y-axis is 90, so we can less 90 from 130, and to give us this as 40 degrees. Now let's see how we can use that triangle. So if we observe the triangle that we've made, notice that what we have is this, and then we have the face parallel to the x-axis, and we have our vector itself. So to observe the directions, of course, you have to go back to this. Observe that fx is in the negative x direction because positive x is in this direction. Fx is parallel to the x-axis, but it's going in the opposite direction. So it's going to be negative. And this is the part that is posing as fx in this side, in this case. Fy is here, and the vector itself, not the vector itself. Notice that the hypotenuse this time is this side here. And this side, when we're looking at the earlier triangle, this side we labeled it as f prime. So even here, the hypotenuse is f prime. Now the angle here, of course, we saw that this was just 40 degrees. So from there, we can come up with an expression for fx in terms of the angle and f prime, and also do the same thing for fy. Fx is opposite to the 40-degree angle, so we're going to be using sine there. And the hypotenuse is f prime, so it's going to be f prime, then sine 40. From here, we remember the expression for f prime. F prime, we found it earlier on. It was the vector itself, cos 25, so we're going to have 1000 cos 25, then sine 40. But when you go back to the original diagram, we see that again fx is pointing in the negative direction, so we're going to drop a negative here. So that's the trick when you're using this approach. But if you decided to use 140 here, 130 I mean, instead of 40, the negative would come on its own. You would not have to put a negative. So you could have as well just said 1000 cos 25, but this time around you'd have to use cos 130. Notice that evaluating this and evaluating this, they give you the same answer. It will be a negative answer, and it will be negative 583 pounds. So when you're measuring your angle from the positive x-axis, then cos can give you the x component, and it will position it exactly in the quadrant where it is with the respective sign. So that's the best thing about using this approach. But I always find creating triangles the easiest approach. So that's the one I stick with. So this gives us the x component, and we go on to find the y component. And from here, the y component is side by side with the 40. So we're going to be using cos here. So it becomes the hypotenuse, which is f prime, then cos 40. Remember again what f prime is. That's 1000. Then cos 25. Then cos 40. The y component is pointing along the y-axis, so this is in the positive direction, so I'll write it the way it is. And if we evaluate this, this comes to give us 694 pounds. So alternatively, we could have obtained the same answer by just saying 1000 cos 25 sine 130. This would have given us still the same answer with the same sign. Okay, we use cos 130. Notice that doing this will give you the same answer as the one above, but this time we're using cos 130. So this will give us the exact answer, and it will place a negative for us. There'll be no need for us to drop that negative. And the answer we'll get is going to be negative 583 pounds. So the next thing that we're going to do is to find the y component, fy. So if we go back to the diagram, we find that fy is side by side with the 40, so we're using cos. So that is the vector itself, or the hypotenuse, which is f prime. Then cos 40, and then f prime again. This is 1000 cos 25, then cos 40. So alternatively, we could have also done 1000 cos 25 and sine 130. And doing this gives us the same answer. So this and this will give us the same answer, and it is going to be 694. So 694 pounds. So now that we have the x, y, and z components, we can then express our vector in Cartesian vector form. So the Cartesian vector form is going to be fx in the I direction plus fy in the j direction plus fz in the k direction. So of course we already have what the components are, so it's just a matter of substituting. So this becomes 583 in the I, remember this is negative, plus the Y component, 694 in the J, then the Z component, plus, and for the Z, we had 423 in the K direction. So that sorts out the Cartesian vector form. The last part was now for us to find the directional angles. So the directional angles are alpha, beta, and gamma. And remember from the previous class that cos alpha is equal to fx, the x component, divided by the original vector f. Since we already know what the original vector is in this case, so I can easily get what alpha is. So it's going to be cos inverse the x component, which is minus 583 divided by 1000, and this gives us 125.7 degrees. So we move on to beta. For beta again, remember it's cos beta is equals to the y component divided by the original vector. So beta itself will be cos inverse, and the y component we found 694 divided by 1000, and this gives us 46. So you have 46 degrees. And lastly, gamma will be cos inverse of 423 divided by 1000, and we get 65.0 degrees. So these are the direction angles. So that sorts out the first example, and we move on to the second example. For our second example, we have this diagram. So in this case, we have three force vectors. So we have F1, F2, and F3. So again, like the previous one, we want to find the components of the resultant. And then apart from that, we want to find the directional angles for the resultant, and we also want to express the resultant force in Cartesian vector form. So to achieve that, there are two methods that we can use, especially for F1. There are two methods we can use to break it up, since we're given those pieces. But for the most part, let's first use the one we're from doing, which might seem to be a little bit longer. But I think in the next class, we're going to introduce a more simpler method that we're going to be using, I think, for some time. So let's see what we have to do. So we have three force vectors that we are combining to get the resultant. So let's use a method that I used in my other videos when we're doing two-dimensional vectors. So since we have three force vectors, so we have F1, F2, and F3. The only difference now is we have three components. So let's separate them accordingly. So we have X here, Y here, and Z here. So for F1, when you look at it, the key here is what they're giving us with these lines here. So these lines are specifying that we are in the ZX plane. So this vector F1, it is strictly in the ZX plane. It has no component in the y-axis. So already by observation, we can see that the component of F1 in the y-axis is going to be 0. So I can place that in advance. But then when we observe also the triangle that we're given here, notice that that's a right angle triangle. And if you look at it, it's something like this. So we have a triangle that is more like this. And when you look at it, the longer part is given as a 5, then the other two sides are given as 3 and 4. So you have a 5 here, 3 here, and 4 here. Now observe the sides. This 3 is opposite to the y-axis, to the z-axis I mean, and the 3 not opposite, I mean parallel to the z-axis, and the 4 is parallel to the x-axis. So I'll come back to that later. But our interest, we want to use these sides to determine the angle that is right here, the angle between the x-axis and the vector force F1. So to do that, so we're looking for this angle here, we can use any ratio really. So we can even use sine. So we can see that that angle there can be obtained by just using sine. We can say theta, if this is theta, will be equal to sine inverse. So sine opposite, that's 3, over hypotenuse. Hypotenuse is 5. So this is literally going to give us what that angle is. And we're going to find the angle there to be 36.87 degrees. So once we've obtained the angle there, then we can go back to determine the components. So we resketch our triangle, but now instead of the sides, we have the force vector F1, and we want to find the components. One component is pointing in this direction, the other component is pointing in this direction. Don't think this is the negative direction, because what we're using is this scale. The component that is here, this is going in the positive x, and this is going in the positive z direction. And the angle that we found is literally this angle here. So we want to break that force F1 into the x and the z. The y is already seen to be 0. So from here, you see that the angle is side by side with the x component. So I'm going to be using cos there. So for the horizontal part, it's going to be F1 itself, and F1 is just 90. So it's going to be 90, and then cos the angle, 36.87. So that will give us the x component is positive, so we'll leave it like that. And the z component will be here. It's opposite to that 36-degree angle, so we'll be using sine. So it's going to be the vector itself, F1, that's 90, and then sine 36.87. So again, this is pointing up, so it will be positive. Next up, so that's it for F1. We move on to F2. F2 is this side. For F2, we see that we have to use that method for when we're given this angle, the one that we used in the previous example, and an angle that is this side. So we're going to be using the same method. So for this part, we can start with either side. We can say, let's first get the z component, meaning I'll start first with this triangle. And what we see there, that's a right angle triangle with the right angle being down here. We'll label this line here as our f prime, f2 prime. And this side, notice that this side is parallel to the z axis. So this is going to be f2 in the z axis. So from here, let's see what we get. So our triangle now, when we sketch it, we have f2 in z coming this side. The base, that was f prime. So that is f2 prime. How do I label it? So that's f2 prime, yes. And this is f2 itself. So the angle that is here, we're given what this angle is. What have they given us there? So that is 60 degrees. So we can then get what these sides are. So this is 60 degrees. What is F2? From the question, F2 is 150 newtons. So we have 150 newtons here. Is it newtons? Is it pounds? That's newtons. So everything here is in newtons. Okay. So from here, we can then move on to get the components. So Fz is opposite to the 60. We'll be using sine. So F2 in Z will be equal to the vector itself, which is F2, 150. That's the hypotenuse. Then sine 60 degrees. This will give us what F2 is. And then we have F2 prime, the hypotenuse, 150. It is adjacent to the 60, so we're using cos. So you have cos 60. So when we now move on to the second triangle, the one down, notice that this will still be used, the F prime will still be used. But now the triangle is coming like this, and then going like that, with the right angle being here. Not necessarily there, the right angle being here. Okay, yes. this is where the right angle is. So this is our F2 in the x-axis. This side is parallel to the x-axis, and this side here is our F2 in the y-axis, and this red line here still remains to be F2 prime. So in this case, we see that we can express F2 y in terms of F2 prime and the angle, and let's do the same thing for F2x. Let's sketch that triangle. So what we have is, we have the side parallel to the y-axis, then we have the side parallel to the x-axis, and we have F2 prime here. So I have F2 prime, then F2y, and F2z. F2x, I mean. So from here, the angle that we have is this angle here, and it's given us, that's 45 degrees. So when we write this, F2 in x will be equal to the hypotenuse, which is F2 prime, then it's opposite to the 45, so I'll be using sine there, sine 45. But when we substitute what the prime is, F2 prime is, so the expression was 150 cos 60, so it becomes 150 cos 60, or this is just F2 prime, then sine that 45. So this will be an expression for F2x, and then we have F2y. F2y, again, it will be F2 prime, the hypotenuse. It's side by side with the 45, so using cos. So when we bring in what F2 prime is, so it becomes 150 cos 60, then this time it's cos 45. So when you look in terms of the direction, F2x is in the positive x, yes, and F2y is in the positive y. So those are both positive. So I can bring the components for F2 in this table. So we found in the x, we had 150 cos 60, and then sine 45. In the y, we found 150 cos 60, and then cos 45. In the z, we had 150 sine 60. So this sorts out F2. We move on to F3. F3 is strictly along the z-axis. That simplifies everything we have to do here, because it implies that it has no contributions in the x and in the y, and the whole of F3 is literally a z component. So we have 0 in the x, 0 in the y, and half F3 goes in the z, and that is 200. So we have our 200 here. Then we can add up. To get the resultant is here. Sum everything here, we'll get the resultant down here. Sum everything here, we'll get what comes here, and so on. So we find that we have 125.03 here, and we're going to find 53.03 here, and finally 383.9 this side. So now that we have the components, we can even get the resultant. So you can even get the resultant force. The resultant force, we know to say that force, the net force, we can even say net, F net, will be equal to, just the magnitude, will be equal to the components squared, then summed up. So you have 125.03 squared plus 50.03 squared plus 383.9 squared. Doing this gives us 407.62 newtons. Okay, now we have found the magnitude of the resultant. We can go right ahead and express our force in Cartesian vector form. In Cartesian vector form, all we need are the components, fx, write it in the I direction, fy in the j, plus fz in the k direction. So our x component was 125.03 in the I. Our y was 53.03 in the j, and our z 383.9. So this is our expression, or our force, in Cartesian vector form. Next up, we have the directional angles. So the directional angles, remember alpha, beta, and gamma. So all we have is, we remember cos alpha, fx over f. So alpha will be cos inverse of fx over f. Substitute, do the math, and you get 72.14 degrees. We move on to beta again, cos inverse fy over f, and this is going to give you 82.52 degrees. And lastly, gamma, which is cos inverse of fz, that was 383.9 divided by f itself, 407.62, and we get 19.64 degrees. So this sorts out our problem. We have found the components, expressed the resultant in Cartesian vector form, and then found the directional angles. Now guys, this brings us to the end of this tutorial. If you have any questions, leave them in the comment section. We'll see you guys in the next tutorial.